Ray model of light. Alright, so this is the next phase of rays and thermodynamics that we are moving towards. Is basically the second to last part of that module. So to start with, we are going to look at an inquiry question. So I'm just going to look at the syllabus outcomes that we are supposed to address for each of them. And as you can see, it starts off with an inquiry question which state that what properties can be demonstrated when using the Ray model of light. And the Ray model of light here, which is a core topic. So in order to do all of that, the first thing we do is to address the inquiry question, and the next thing we're going to look at, according to the syllabus outcome, is to look at this aspect which says here you should conduct, as a student, a practical investigation to analyze the formation of images in mirrors and lenses via reflection and refraction using the Ray model of light. The next thing the syllabus requires us to do is to conduct investigations as well to examine qualitatively and quantitatively the refraction and total internal reflection of light. So we have actually talked about some of those properties of waves, but we dealt with that generally on the waves. Now we're trying to look at that on the light. So let's have a look at that. The other thing that we're going to be looking at. So again, the next part is to predict quantitatively using Snell's law, the refraction and total internal reflection of light in a variety of situations. And then we are also going to conduct a practical investigation to demonstrate and explain the phenomenon of the dispersion of light. Some of that we've done that, some practicals as well in the lab just recently about light, but we haven't addressed it directly under the Ray model of light. Second to last part, we are going to also look at an investigation to demonstrate the relationship between inverse square law, the intensity of light, and the transfer of energy. So that's pretty much close to the end of the syllabus. And finally, we have to solve problems or make quantitative predictions in a variety of situations by applying the following relationships. So these are the relationships here, as you can see. So for the refractive index of a medium x or Vx is the speed of light in a medium. So this is what we have here, and then we have Snell's law applied here in these equations. We're going to look at all of that. Also to compare the intensity of light at 2 points, R1 and R2. We started looking at some of those on the waves, but we're going to dive into that in terms of light. All right, so that's that for what the syllabus requires us to do. Now let's start to look at each of the points one after the other. The very first thing we look at here is the inquiry question. Under the inquiry question, it says what properties can be demonstrated when using the Ray model of light. So what sort of properties can we describe or can we see when you're using the Ray model of light? So the Ray model of light allows us to describe many of the observed behavior of light. We know, I think we talked about some of that. We've done some experiment about reflection, about refraction, about the critical angle and dispersion. We did some experiments a while ago about using the ray box, for example, and we used a number of concave and convex mirrors to look at how light is reflected on all of those surfaces, and where we can actually determine the position of the focal point and things like that. On a plane mirror, we talked about things like the norma. You guys know what that is. And also we talked about the angles of incident and angles of reflection. So these are just some of the properties of light that we can demonstrate using the Ray model of light as well. Okay, so this is not entirely new in terms of what you already know. It's just another dimension to look at light, particularly as a form of wave. So now let's have a look at light. What is light? Light is a term commonly used to describe a small part of the electromagnetic spectrum, which is usually we call it the visible part of the electromagnetic spectrum, as you can see here. So this is the electromagnetic spectrum, and here we have the visible part of that spectrum, which is essentially what light is. Why is it light? Because it's that part that we can see. Okay, so it's a small part within that region, which ranges from 400 nanometers to 700 nanometers. So these are the range that we can actually see. All right, now in terms of frequency, in terms of wavelength, so that's the range of wavelength that we can see visible light. So visible spectrum is a range of electromagnetic radiation we can see in the electromagnetic spectrum, as I just highlighted. Now, the electromagnetic spectrum, let's have a look at it in a little more detail. So here, the spectrum is variations in the frequency and wavelength of light changes its properties. So variations in these two properties, we've done that in terms of waves, in terms of the wave equation. We have frequency, wavelength, and we have the period as well. But here we're looking, our focus is mainly on the frequency and wavelength. So these the variations in these two quantities of light changes the properties of light. So that is what we are seeing here. So as you can see here as well, if we look at a bit more diagrammatic form of the spectrum, we have radio wave. As you can see, the wavelength is very, very long. So as you go along the spectrum, the wavelength start to get shorter, and the shorter the wavelength, obviously you know that the wavelength is basically the distance between a trough, one trough and the other, or one crest and the other. So therefore, as you can see here, as you go towards the right hand side towards gamma ray, we had the frequency, the wavelength getting shorter and shorter, and the shorter the frequency, sorry, I'm mixing up the two terminologies. The shorter the wavelength, the higher the frequency. So that means if you look at these waves over here in terms of gamma rays, these are very weak, and these, as you come towards gamma rays, they get stronger because they are very, very intense. They come at very high frequencies. Again, just like we talked about sound waves, that was the last thing we talked about. The higher the frequency of the sound wave, the higher the pitch, and therefore the more impact that might have on your hearing. So therefore, sometimes when you're standing closer to an object that is producing sound and the frequency is higher, you kind of perceive the sound much louder compared to someone standing far away. So the same thing happens with these ones here. These ones are producing gamma rays, X-rays. That is why we use them in medicine. They are also very dangerous to our health in the sense that we need to have protection because of the amount of energy they produce, and that is the reason why they tend to be very dangerous, because of the high energy they produce. So we're not going into that right now. We're just looking at the different wavelength in terms of these different waves in the spectrum. So now the range of colors that we can see correspond to a range of different wavelengths, and therefore frequencies of light. Yeah, so as you can see here, we have infrared. The wavelength correspond pretty much to the frequency here. So the longer the wavelength, the lower the frequency, obviously. Here, red light has the longest wavelength, as you can see, and also the short, and the wavelength is shortened through the rainbow to violet with the shortest wavelength. All right, so towards violet with the shortest wavelength. So visible light is just one small part of, as I already mentioned earlier, that it's just a small part of the electromagnetic spectrum, and it also includes radio waves. So there's electromagnetic spectrum, obviously, as you saw here in the previous diagram, has all of these gamma rays, X-rays, ultraviolet, and so on and so forth, radio waves and things. So this image here is just a more diagrammatic form for you to really be able to see how these waves look like. All right, I'm not going to waste a lot of time on that. So let's have a more detailed look again at electromagnetic radiation. So as you can see here, we have a magnetic field and also an electric field. They are also moving in the same direction. So both are interacting from the source here where we've seen the light source. These two fields are involved, and the two fields also are moving in the same direction. So here it says electromagnetic radiation is energy that propagates through varying electric and magnetic fields. So as you can see here, the fields are changing as they propagate. Okay, so as they move from the source here, the fields, magnetic field and the electric field are changing. So more like a sine wave, as you can see. So both of these fields take the form of transverse wave, which travel together. As you can see, transverse wave perpendicular to the normal in this case here, or the wavefront. Now, their frequency and wavelength might vary, but they vary proportionally according to the equation. So here, this is similar to what we've dealt with before in terms of other waveforms that we dealt with. This is a wave equation. In this case now, in terms of light, we have C. So C is equals to frequency times lambda, where in this case C is the speed of light. So that the speed is always the same. So in this case, it doesn't matter what happens here. Frequency and wavelength, whether they change, the speed of light doesn't change. It stays the same in all mediums. So note that. That is going to be part of an exercise you're going to do at the end of this lesson. So the sources of light, let's have a look at that. Now, sources of light can be luminous. I think you may have come across this terminology before. Luminous bodies are those that emit electromagnetic radiation in the visible part of the spectrum, either as a result of chemical processes or because they are incandescent. So we have, for example, incandescent objects glow because, so I just define this terminology here, incandescent. They glow because they are hot, and the hotter they get, the more light they produce. So incandescence is actually one of the principles behind some of the energy saving globes that we use today. All right, so the hotter they get, the brighter they become. So the same thing happens in the light globes that we have. The same thing happens in the sun, for example. So these are luminous objects. The sun, the light from the candle or tungsten filament in the bulb that we have in our homes to give us light. And then the other part, the other source of light can also be non-luminous or illuminated. What does that mean? It means objects that do not naturally produce light, either through chemical reactions or through basically just through glowing or getting hot, for example, I should say. So here, these objects basically depend on other sources of light. In other words, they depend on luminous sources of light to produce light. So in other words, they basically just reflect light from luminous objects. An example is the moon. At night, we always see the moon shining. Why we see the moon shining? Sometimes you might wonder, where is the moon getting the light from? Is it actually burning hydrogen in its core, just like we have the sun? No, it doesn't. What it does, it's basically a piece of rock that is capable of reflecting the light from the sun. So that is why we see the moon glowing at night. And so true that at night, just like we know that in different parts of the world we have day and night. Currently in Australia at this time is about 7:22 p.m. at night time. In other part of the world it's just starting a day. So the sun is constantly on, and because of that, the part of the world that is usually facing nighttime get a reflection from the sun, from the moon. So from the moon reflects the sun's ray. And therefore, at night, we see the moon shining. And you might think that, oh, this moon is given light out. It's not luminous. It is non-luminous, so it just reflects light from the sun. All right, not talking too much on that. We move on to more important part. So here we are looking at wave and particle. Modern theories say that light behaves as both a wave and a particle. All right, now the wave model is used to explain how light propagates and how it interacts with objects at macroscopic, that is visible to the naked eye scales. So here, why do we call it a model? Because models, I think I gave a video in our previous lesson about using models. Models are basically just things that we use to be able to visualize um, uh, phenomena that we cannot generally see with our naked eye. So something similar to what we are seeing here in terms of motion of the wave here, as you can see. So this one is just a model, also explaining to us how the wave actually propagates. So as you can see, they're moving in one direction, and as they move, they are changing. So because they're changing, they're going a sine wave format. That actually makes that is how the waves propagate. So in this case here, we have a definition of propagation is basically to move or travel, often used to describe wave motion. So as you can see in this diagram. So the particle model is used to explain how light interacts with materials on microscopic scales when it is absorbed or emitted. So the same thing like the light we see in the sun, or maybe if you have light in a dark room compared to light interacting with other colors of different objects or different materials, what happens when they interact. Now let's have a look at this here. What kind of wave is light? What do we think is what type of wave is light? So from its properties, light behaves as a transverse wave. All right. So however, it can travel through a vacuum, so it is not a mechanical wave. So here, for example, you can see the sun's light coming from space, traveling through the vacuum of space. So in this case, it doesn't need a material to move. As a result of that, it is not considered a mechanical wave, because mechanical waves require a medium to propagate. So without a medium, mechanical wave, an example is a water wave, for example. So the waves in water cannot move without the body of water to actually propagate, to move from one end to the other. So they need a medium. So mechanical waves moves by moving particles, so it requires a medium to propagate, as I gave you an example earlier. Transverse wave is where the vibrations of the wave are perpendicular to its overall direction of motion. All right, so as you can see, the sun's light coming towards the earth. We can reference that directly from the position from which you can see the sun, and it is perpendicular. That is the reason why we see the horizon, as you can see over here. It looks like a flat horizon because of that property of light being a transverse wave. So the speed of light in a vacuum, it's generally given to us. That's the actual figure there, but we generally approximate that to 3.00 times 10 to the power 8 meters per second. So don't forget that. That is part of what you will be using in your formula sheet as well. Now, the ray model of light. Let's have a look at that. That's the actual topic that we are looking at. So light always travels radial, just like here, as you can see. It's moving all around. So it goes in every direction outwards from a source. So this is a source like a light bulb in your house, for example. If you put it on, you see what happens. Now, this means that light is always made up of spherical wavefront. So spherical, in a sphere, just like we can see here. And these wavefront, what they actually mean is that the waves are moving in a sine wave format. So if we include all the sine waves on these different rays, as you can see here, it's going to be very, very messy. So we will not be able to actually see what's going on here. And that is the reason why to draw array diagram, we exclude the wavefront just to make sure it's easier. So it says the light travels radially out from a source in all directions. All possible rays cannot be included, as this will make the diagram unreadable. So again, not only the wavefront, but we can't include all the rays because they're just too messy. So we just select the ones that are relevant to our discussion, and then we focus on those. All right, next one, rays of light. Again, as I said earlier in the previous slide, we are looking at objects here. We can only see these objects if the ray that comes from them can hit our eye. So here, for example, if you look at this diagram here, there's a yellow object over here, and there's a person standing here. The rays from the heart is hitting the eye, so this individual can see the heart, but they cannot see this object because the ray from this object is not hitting the eye because of the position they're standing. It's like you're standing with your back against your friend. You cannot see your friend because the light that is coming from them is not hitting your eye, it's hitting the back of your head, and your eye is not at the back of your head. So for you to see them, you have to really turn around and face them directly. That way you can see them by perceiving the rays that come from them. So that is why light actually travels in a straight line. Okay, so here, rays of light make it easier to study the properties and movement of light. A ray can be thought of as an infinitely narrow beam of light, just like those ones here. Light rays from a source radiate, travel outwards in all directions, as we talked about earlier. And obviously, the fact that they travel in a straight line allows us to see object. But then we can use those properties as well to be able to see object, or we can trick those properties around, like we do, for example, in reflection on curved mirrors or on flat mirrors and things like that. I think we talked about those the last time when we looked at mirrors and the advantages of concave and convex mirrors that are used in our cars or blind spot and so on and so forth. So again, it's a trick that we use to bend light in some form to be able to use light to see objects that we normally wouldn't be able to see as a result of the fact that the light travels in a straight line. All right, now let's have a look at geometric optics and image formation. Again, as I was mentioning in my previous comment about concave and convex mirrors, this is where this brings us, because we cannot talk about the ray model of light without talking about the geometric optics and image formation. So image formation using lenses, again, geometric optics uses a ray model of light to analyze image formation from mirrors and lenses. Rays parallel to the principal axis are refracted to a focal point. We know that. We've talked about that in our previous discussion in terms of rays, in terms of waves. Focal point, at which a point at which waves meet after reflection or refraction, and then the distance between the lens and the point where the rays that are approaching the lens parallel to the principal axis is basically referred to as the focal length. All right, now let's have a look at more aspect of geometric optics. So an image is that point where the rays that reach our eye appear to emanate. All right, that reach the eye, should be the eye there. So that was a little typo there. An image is that point where the rays that reach the eye appear to emanate. So that's essentially what that means. If I look at this computer screen, I'll see this computer screen as a computer screen because light is coming from the computer screen that hits my eye that allow me to see the computer. So I cannot describe that as an image until I can perceive light from it to tell me what it is. So when the rays actually converge to a point, we say the image is rare, like I'm sitting here looking at a computer, or when you sit in a lounge room looking at your TV, for example, you can see the TV for what it is. You can see the size, you can perceive it because it's a real image, because the light is coming and then we can see it's not falling behind the focal point. So an image, a rear image will appear on a screen if placed at the front of at the point of convergence, such as in movie theaters. Of course, like when we see movies in movie theaters, image is projected on the big screens as well, like from our projectors. Yeah, that's a practical example of that, because the images are rare, so we can see them as they are. So the image may be larger or smaller than the object. Again, that is the reason sometimes we use magnifications. The same thing happens in our eyes. We are going to deal with that a lot more. Sometimes as we grow older, the lenses in our eye get weaker, and therefore we need to have magnifications at times. Or when images are far away, use a binocular to be able to pull the image closer, because it's trying to magnify the image so you can see it from a longer distance. So in this case, magnification is the ratio of the height of the image to the height of the object. So as you can see over here, so object here, this is the image location over here, rear image formed by a convex mirror. So in this case, the eye is here. The eye can see the image of the object here, simply because the light that comes from the object converges at this point to make it possible for the eye to see. All right, and this is why we can see that image as rare as it is here. So let's have a look at the other part. The other part says, when rays appear to converge to a point that rays cannot actually reach, example behind a mirror, like in terms of a concave mirror, then we cannot see where the light is going to fall. We can just imagine where that point is, and that is the reason why we call that sort of image as a virtual image. Virtual image in the sense because it's not rare, we cannot see it, and those sort of images cannot be projected on screen. So the position and type of image formed by lenses and mirrors can be determined by using the principles of geometric optics to draw ray diagrams. So basically, geometric optics is all about using drawing ray diagrams using those different principles of like concave and convex mirrors, and also trying to work out where the focal point is, or where, if there's a focal point or there's no focal point of convergence, if the image is real or not real. So we're using all of these principles, and that the act of using those principles to see an image or draw an image is what geometric optics is all about. All right, so this brings us to the end of part 1, and now I have also included some tasks online that you'll be working on to complete in conjunction with today's lesson. So part 2 of ray model of light is coming up. I think that should be in our next lesson. All right, thank you so much. I hope that helps.